This is now the third practice exam in this series I'm doing for Math 31A. This professor gave a exam or a packet of 4 exams, so this is the third one now. And at this point, even if you don't have this professor, I really don't know if this professor even still teaches at UCLA or not, but this is just a general study strategy. Hopefully by this point, this is already the third exam, you noticed the common questions the professor asks. So for example, there's of course going to be limit questions. There's of course going to be derivative questions, simple chain rule questions, implicit differentiation. Those you can always expect. Intervals of increase and decrease, like in this function, concavity. Those are the common things, if you notice so far, in the exams, and you'll notice again in this exam. Another one like volume, shell method, Washington method. So the professor, especially if it's your professor, and if he or she gives practice exams and multiple of them, you can see the common types of questions they ask because they're the topics that they want you to know. Okay? So with that said, let's begin with this exam. Okay? Number 1, find the critical numbers at intervals of increase and decrease. So when the function talks, when we're interested in increase, decrease, that's the first derivative test. So let's take the derivative of this guy. We need the quotient rule. Okay, so bottom d top minus top d bottom over bottom squared. Start simplifying, and then here, we can factor out x. Why do we want to do that? It's easy to get our critical numbers or critical points when it's factored. Okay, so the critical points are 0, -16, and -8. Because critical points are when the first derivative is 0, so that's when x is 0 and x is -16, and when as well when it's undefined, so when x is -8. You divide by 0, it's undefined there. Okay, so those are critical numbers or critical points. All right, now I always just draw a number line to do the sign test now. Put your critical points as tick marks. Okay, now we go interval by interval. So in this interval from -infinity to -16, we plug in some number, like a huge negative number. What's the sign of the first derivative? We can plug in from here. Huge negative number. So this would be negative, this would be negative. The bottom is always positive, notice, because something squared is always positive. So we can ignore that actually. So 2 negatives make a positive. Plug in a number in this interval, like -10. This is negative, this is positive. There's 1 negative, so it's negative. Plug in a number here, like -1. This is negative. This again is positive. So there's only 1 negative, so the sign is negative. Plug in a huge positive number. These both would be positive for sure. It's positive. Okay, so increasing, the function increases when the derivative is positive, so in those two intervals. And the function decreases when the derivative is negative, first derivative. That's these two intervals over there, and that's why I wrote over here, typed over here. This is a volume question. Let A be the region of the first quadrant bounded by the curves y equals cosine x and x equals pi/4. Write the volumes of the solids, but don't evaluate, okay? So, first one, solid formed by rotating A about the line x equals 0. So as always, you should sketch this region first. Cosine x looks like this in the first quadrant. Okay. Technically it repeats, right? But you can just cut it off there because our next line, x equals pi/4, is a vertical line right here. Okay. By the way, this point over here is pi/2, if you remember, so that's why I knew x equals pi/4 is over here and this one curve, okay? Or one part of the cosine curve. Okay, so this should be your region over here because it should say bounded by curves, this in the first quadrant. Yeah, so like that. So we're going to rotate it about this line, x equals 0, a vertical line x equals 0. Okay, our functions are in terms of x. We're rotating about a vertical axis, so we might want to use the shell method. Okay, so I draw a representative height of each shell and a radius from the axis of rotation to the shell, the represented shell. Okay, what is the length of h? That is just the function cosine x, right? And what's the length of r? That's just x. Okay? So that's this part over here. So you have to remember the shell method is 2 pi integral RH dx. Okay, so again, r is this length here, which is just x. H is this length here, which is cosine x. Okay, limits of integration. We're integrating in terms of x, so it starts at 0, ends at pi over 4. Okay, now this one, solid form by rotating a about the line y equals minus half. So here's the region once again. Sketch the axis of rotation. Y equals minus half is this horizontal line down here. Okay, we want to use the Washer method here because we're rotating about a horizontal axis and our functions were in terms of x. Okay, so from the axis of rotation, draw a representative r to the further curve and to one more to the inner curve. In this case, the inner curve is just the x-axis. So notice, again, that's why it's helpful to sketch the region. Maybe shade it like I did over here. Draw the r out from the axis of rotation to the furthest in the region, r in from the axis of rotation to the closest line in the region, okay? So the way to do Washer method is pi integral r out squared minus r in squared dx. What is the length of r out? Here, instead of memorizing it's a plus or minus, just realize that this length from here to here up to the axis is cosine x. But we have this additional amount here. How much is this additional amount? Is it not half? Because this line is minus half. So from 0 to minus half, that's the length of half, right? So that's why it's cosine x plus half. Okay? Or if you really want to memorize, it's outer or upper minus lower again. In this case, it is cosine x minus negative half, which becomes the plus. So again, you can memorize if you want. I don't prefer that. I just prefer to understand that this is a length. So this length is cosine x. This additional length is half. Okay, and when I started understanding it like that, I never got it wrong. I didn't have to guess if it was a minus or plus. Okay, now for Rn, what's this length? That's easy, that's just half. Okay, oh, I forgot my limits of integration actually, so let me fill that in. It should be the same limits as up here, because we're integrating in terms of x. The start is 0, stop is pi over 4, so let me add that in. 0 to pi over 4. Okay. We're asked to differentiate. This is a typical chain rule problem. Tangent of half sine of x cubed plus 2x. Differentiate the outermost function first, which is secant squared. Keep everything on the inside the same. Now we move inward times derivative of this. Derivative of sine is cosine. Half is just a constant, so we leave it alone. Derivative of sine is cosine. Okay, keep the inside the same. Times derivative of the inside. What's the derivative of the inside? That's 3x squared plus 2. Okay, this is a simple chain rule problem. Part B, oh, this is a fundamental theorem calculus problem. This is always the easiest points, in my opinion. Okay, so how do we do fundamental theorem calculus? I go through this, I say this every time. If you've seen my previous videos as well. Plug in the upper bound as your variable of integration. So x cubed to the 1/3 is just x. X cubed to the 2/3 power. 3 divided by 3 is 1 times 2, so x squared. Okay, times derivative of the upper bound minus plug in the lower bound times derivative of the lower bound. This is the procedure. Very easy, as you can see. So now you just start simplifying. Mainly, you just need to calculate these derivatives, which is, this would be 3x squared, right? Combined with the x, that's 3x cubed. This is just 1, right? So we just have that. Okay, easy points. Don't miss out. Write in mathematical symbols the meaning, let me block this, of f of x is continuous at x is equal to a. This is just testing if you know the definition of continuity, which is this. Very easy. Limit as x approaches a, f of x is equal to f of a. Okay, this is, if you see my other videos of this professor's practice exams, this is not seen before, so this might be the deciding question to determine the students who get an A versus get a B versus get a C and all that. This might be one of the questions. Okay? They usually like to throw in a weird question to challenge students. Okay, how about part B? The meaning of f of x is differentiable at x is equal to a is that the limit, this guy, exists. This is the limit definition of derivative, right? One of them. Since the limit of the denominator is 0 and the limit of the quotient exists, the limit of the numerator must also be 0. Complete the proof of differentiability implies continuity using properties of limits to prove that if limit as x pushed a, right, then f of x is continuous at x is equal to a. Okay? So, what is this weird question asking? Even I was confused at first, but the key points were complete the proof that differentiability implies continuity using properties of limits. That's key. How can we use properties of limits here? Is what it's asking. To prove that if this, then f of x is continuous. So somehow you have to probably get from this to this. How in the world would you do that? By properties of limits. So let's try that. We can distribute this limit to each one individually. Okay? This is just a constant. So the limit of a constant is the constant. Okay? Now just move this f of a to the other side. And you're done. See, this question was actually really simple. This was a weirdly worded question per se, because you've never seen it before. But look how easy this was. Right? If you just had to know this, honestly, and you're just matching this to that. And we just use a simple property of two properties of limits, actually. Okay? This one's actually new as well. Find the average value of the function on this interval. Average value is quite easy points as well. 1 over the length of the interval, so 6 minus 2. Integrate over the interval 2 to 6, the function, f of x dx. Okay? This is average. So remember, average is you sum up all the terms and you divide by the number of terms. This is kind of the same. Integral is a sum, if you remember. So you're summing up all the values of the function and dividing it by the length of the interval. So it's kind of similar, right? So that's how you can remember the average value formula. Okay? This is 1/4. Okay? 1 over 6 minus 2, that's 1/4. Now over here, you can substitute. Let u be 2x minus 3. Okay? du is 2 dx then. And then we can substitute x as well. We just rearrange terms here a bit. X is u plus 3 over 2. And don't forget to change in limits, but I always do that afterward. So 1/4 is from there. X dx. Just x is u plus 3 over 2, or half times u plus 3. The square root term is just square root of u, or it's u to the half. Dx is du over 2, or it's half du. Okay, let's pull all the halves out. Okay. Oh, I forgot to go over changing the limits. So x is 2, u is 4 minus 3, which is 1. X is 6, u is 12 minus 3, which is 9. Okay, so don't forget to change the limits. Okay, so now you just start simplifying. So I pulled the halves out, distribute this u to the half to both of those. All right, and then this is just power rule and then fundamental theorem calculus afterwards. So this should be the final answer. So you can see I didn't even bother simplifying, probably because the professor didn't even care about simplifying. Find the radius and height of the right circular cylinder of largest volume that can be inscribed in a cone whose height is 5 meters and base is 2 meters. Base radius is 2 meters, okay? So it might be helpful to sketch what's going on. So that's what I did over here, okay? Right circular cylinder inscribed in a cone. So I kind of sketched it like that. Here's the cone. You can see it's in the middle, right? The cylinder inscribed in the cone, okay? And the height of the cone is 5. The radius of the base of the cone is 2. So that's what I did there. Okay? By the way, this is an optimization problem, not a related rates problem, because it's telling us to maximize or minimize, right? Largest volume. We're maximizing volume. Okay? If it was a related rates problem, they give us like rates and all that. But here they didn't give us any rates, actually. Okay? Okay, so the whole point is to optimize volume. So we want an equation for the volume. Okay, so V equals pi r squared h. We're optimizing the volume of the cylinder. This is the formula for the volume of the cylinder. So we need to get V in terms of one variable to easily differentiate it. Otherwise, you would have to use like implicit differentiation, or if it's not a function of the same variable, like r is not a function of h, or h is not a function of r, it's a function of a different variable, then you have to use multivariable calculus, which you don't know at this point. So the point is, you need to find another equation somehow to write v as a function of just one variable, not r and h. Okay? How in the world would we do that? That's the challenging part of this question, actually. Okay, so let's go over here. So if I just take a cross section of what's going on here, so I slice it, okay? So this part is like the cylinder over here. So when I slice it, right, it's like that. And the cone would just be like triangular, right? So what's going on here? How can we represent r and h? R in terms of h, or h in terms of r. Okay? So we know that the height of this whole triangle is 5. That's given. Okay? The height of the cylinder is, let's say, h. Okay? H. So what's this remaining over here? It's 5 minus h. Okay? And the base of the radius of the cone is 2. Okay? And we can have a radius for the cylinder as well. We call it r. Technically, this amount that's short is 2 minus r, but we don't need it. Why don't we need it? Well, we can draw two similar triangles, actually. Okay? So there's a triangle from the cone, like that, okay? So height is 5, radius is 2. This is this blue one on the side over here, okay? And we can draw another one right here, actually, up here. Okay? So the height is 5 minus h. And over here, the base of this triangle is the radius of the cylinder, r. How do we know this similar, by the way? It's by angle, because this angle and this angle would be the congruent, because it's parallel lines, and this is the, I forgot what the term is, but they're congruent because these are parallel lines, okay? And then the right angle itself is congruent as well. So therefore, the third angle is the same as well, and if all angles are the same, they're similar. Not necessarily congruent, they're similar. And that's what we're going to use here. If they're similar, then the ratio of the sides are the same. Okay? So 5 minus h over 5, this ratio is the same as r over 2. Is that what I did over here? This doesn't look right. I don't think this equation over here doesn't look right now that I realize it. But even though the answers are all correct, so it's just a small mistake. Let me grab my blue pen to fix this. So it should be the ratio of 5 minus h over 5, as I said, is the same as the ratio of r over 2. Okay? This is the correct setup. You can see that it's the same equation if I just move terms around, but to explain it, similar triangles have the same ratio of sides. Okay, so this is the correct setup. Okay, but then the math holds. So I cross multiply and solve for r. So r is 10 minus 2h over 5. You can solve for h as well. I just decided to solve for r. I think the professor solved for h actually. So if you happen to have a hold of this exam, I mean, I found it online, so you can easily find it probably. He solved it in terms of h, so you can look there if you want. But this works as well. I solved for r. So r is in terms of h now, so I can rewrite this volume equation as one variable. So I keep my h, but then r I write in terms of h, right there. Okay, and then you start simplifying a little bit to make your life easier. Okay, now we differentiate because we want to optimize. V prime is, this is a constant, leave it alone. We need a product rule here. Okay, set it equal to 0 to optimize. Okay, now how do we solve this complicated beast over here? Well, it's 0 over here, so you can multiply by 25 over pi, first of all, and then that would get rid of this over here, and it'll still be 0 on that side, right? Here I started simplifying, actually, right? Minus 4h, and this I moved down there, okay? Now I can divide both sides by 10 minus 2h, okay? And then again, this side will still be 0. So if I divide by 10 minus 2h, this would go away, and we'll still have 1 power left there. Now I solve for h, it's much easier here, right? H would be 5/3. Don't forget your units, actually. I feel like the professor always forgets his units, so don't forget them. I would mark off, take off points. Okay, so we got the height. We also need the radius, because that's what the question asks. So to get the radius, you just plug back h into here. So r would be 4/3 meters. Okay, so this one was tricky in that you had to be able to recognize the similar triangles. Okay, so whenever it's one of the similar triangle problems, it's usually one of the harder ones, actually, for optimization or related rates. So this is probably another decider question of who gets an A, who gets a B, and all that. Okay, show that the inequalities are true. So first one, the sky is less than or equal to 3√3 over 16. And the professor gave a hint. What is the maximum of that function? So let's not use that hint. Let's use that hint to our advantage. Okay, so to get a maximum, we need to differentiate. So let's take this derivative. We need the product rule. Okay, that's what I did down here. But I guess I was looking at domain again first. What's the domain of the sky? So I guess I didn't complete it over here. Or I did, but I didn't do the test. So let me do it live now. So the domain, what's under the square root, has to be greater than or equal to 0. Okay, that's just the rule for square roots, right? So you can factor out x. So x is 0 or 1. That's when it's 0. So let's put those tick marks, okay? So we can't do anything less than 0 because it will be a negative number, right? We can even confirm when x is -1, for example. Actually, we're checking from here. Okay, let's check from here, actually. Let's not get confused with there. So let's check from here, because we're trying to solve this inequality right now. So when we plug in a huge negative number, this would be negative, this would be positive. So the sign is negative. We plug in a number here, like half, in this interval, like half. This is positive as well, okay? We're playing a huge positive number. This is positive, but this is negative. So it's negative. So the only interval that satisfies this inequality, that it's positive, is between 0 and 1. And we include the ends because it's equal to 0 there. Okay? So why did I get the domain? Well, it might be helpful for when we find the critical points during the first derivative test. Okay, so we want to differentiate this using the product rule, as I said earlier, or I guess, yeah, I used the product rule here, okay? So derivative of square root is 1 over 2 root x, so 1 over 2 root what's on the inside times derivative inside, okay? And this x is from there. Product rule first, d second, plus second, d first. So second, d for derivative x just 1. We start simplifying, so what exactly did I do? So these I combined and I factored out 2 square root x minus x squared. So clearly that would go away from the first term. That's why you still just have the x and this guy. This guy, I factor minus half. So it would be half minus half, which is half plus half, which is to the first power now. Okay? And I factor out a 2. There wasn't a 2 there originally, so there goes the 2 there. Okay, now you just start distributing and simplifying so that you get this. Okay, so I won't go through all the steps, but here, and then you can factor out x, it looks like, right? So the critical points here are 0, 3/4, and 1. Okay, why is 1 here? Well, that makes the bottom 0. And we can't divide by 0. Remember, the critical points, I think I said this earlier as well, are when the first derivative is 0 or when it's undefined. Okay, so that's why we had these three. But coincidentally, these are also those points we found up here when we were checking for the domain. Maybe not a coincidence, actually. But anyway, let's put the points on a line again. Okay. Because the domain is between 0 and 1 only, we don't have to plug in anything here or here. That's why it's helpful to get the domain. So you just got to check these two regions over here. So we can plug in like 1/4, for example. This would be positive. This would be positive as well, right? And the bottom's always positive because we have to square root a positive number, right? So we can only focus on the top. So as I said, these two are positive, right? So that will be positive. We plug in here like 0.9 or something like that. This would be positive for sure, right? This one, what happens here? When it's 0.9, it's really close to 4. So now just imagine 0.9999999 repeating. Really close to 4. 3 minus something really close to 4, that's negative for sure. Okay, so that's why it helps to just pick easy numbers, or maybe go extreme, as you see. I never really pick an actual number in most cases, if you've seen me and observed how I do these problems. Okay, so this is the sign of f prime, by the way. So, because f prime changed from positive to negative, that means there is a max here. And it's the absolute max, actually. Okay, what's the value of that max? So f of 3/4, if you go through the math, it's actually that value up here. So therefore, that function is less than or equal to its absolute max. That makes sense. Okay, so that's that one. This one, integral 1 to 2, square root of 1 plus x to the 4th dx is greater than or equal to 7/3. So technically, you can solve this if you know more integration techniques. Like you can do tricks probably. But you don't know that yet in this course. So you probably learned a comparison test. So we can compare this guy with this guy over here. Because square root of 1 plus x to the 4th, you could probably guess that it's greater than or equal to square root of x to the 4th, right? Because you're adding something, so it's going to be bigger. Okay? And remember, square roots are always positive. So when you add something, it's going to be bigger, right? Maybe not by much, but it'll be bigger by a little bit at least. Okay? Now let's evaluate this right-hand side. Okay? We can simplify. Square root of x to the 4th is x squared. Okay? We're going to assume we don't need plus or minus because we're in the positive, by the way. Okay? In the positive limits of x. Okay. Here, just do the power rule and fundamental theorem calculus, you get 7/3. Not a coincidence. So therefore, the original integral, it is greater than or equal to 7/3 by comparison. Okay, so this one you just had to think of what did you learn in this class? And in the integral section, you should have learned comparison test. And there's the inequality, so that might be a good idea. And a good test-taking strategy. If you really have no clue how to approach this, just really recall the things that your teacher, professor, instructor went over. And it has to be one of those things. There's a number c greater than 0 such that the area between the curves y equals x to the 4th and the line y equals cx is 96/10. Find the value of c. Okay, so area between curves is useful to sketch the region. So let's sketch it. X to the 4th looks really close to a parabola, right? Looks just like it. And it says c is greater than 0, so it's going to be a linear line with positive slope. It looks something like that. Okay, let's find the points of intersection. Because area is upper curve minus lower curve, that's easy, but we need points of the limits. To get the point, and to get the limits, we need the points of intersection, is what I'm trying to say. So let's set these two equal to each other. Okay? And move the cx to the other side. You can factor out x. So x can be 0, or x can be cube root of c. X is 0. This one would be cube root of c then. Okay? So let's set up the integral. 96/10, that tells us that's the area between the curves, equals integral from 0 to cube root of c, upper curve, which is cx, minus lower curve, that's x to the 4th. Now we go through the motions, power rule for both of these guys, fundamental theorem calculus, Solve for C. You can go through the algebra yourself. C is 8. Okay, so this one's actually quite simple. The equations below define curves y. For each equation, calculate the value of the second derivative y double prime when x is equal to 0. Y is integral from 1 to x, 3t over t cubed plus 1 dt. Whenever there's a limit that it's a variable, usually you want to use fundamental theorem calculus. And I went over this in this video already, right? Plug in the upper bound times derivative of the upper bound minus plug in the lower bound times derivative of the lower bound. In this case, the lower bound is a constant, so that minus term would go away. Okay, so we just do the first one. Plug in the upper bound times derivative of the upper bound, which is just 1, times 1. So y prime is this. Okay, so y double prime, that's what they want. We need the quotient rule here. So bottom d top, derivative of 3x is 3, minus top d bottom, derivative of this is 3x squared over bottom squared. Okay, we're asked to evaluate it when x is equal to 0, so let's do that. Y double prime of 0 is, when x is 0, we have a 3 for the first term. This will all be 0, and we have 1 at the bottom. The answer is 3. All right, now sine y is x cubed. We need to implicitly differentiate here. Okay, so we probably want the y value when x is 0. So let's plug in x is 0. So sine y is 0. So y equals 0 is one solution. Technically, there's infinitely many solutions. Like y can be pi, or 2 pi, 3 pi, 4 pi, so on and so forth. Negative pi, negative 1,000 pi. So this is not a good question, in my opinion. It makes the professor's life harder. But let's keep things easy. Let's keep y equals 0. Okay? Actually, I don't think the professor even plugged in and found an actual value at the end, if I remember correctly, in his solution. So this is the proper way to do it, in my opinion. Okay? And yes, I'm saying the professor did not do it correctly. And this is already a bad question. As you can see here, there's infinite many solutions. Okay, so let's implicitly differentiate. Derivative of sine is cosine, but we differentiated y, so we need to tack on a dy dx. X cubed is just 3x squared. We start off with dy dx, that's this. So we can evaluate dy dx at our point 0, 0. So dy dx would just be 0. Easy enough, right? 0 divided by 1, 0. Now we differentiate this, again with respect to x, we need the quotient rule. So bottom d top minus top d bottom, we differentiate at y, so we need to tack on a dy dx over bottom squared. Okay, so now we evaluate again at 0, 0. Okay, so we plug in, so y is 0, x, so cosine 0 is 1, this would be 0. By the way, for this one, we plug in the value we found over here. dy dx at 0, 0 is 0. We found that in the previous step, right? So we can plug in, or previous portion, previous step. So we can plug that in there as well and divide by 1. So the answer is 1, and that's your final answer. Okay. Well, that was number 9. Okay, last one. This one's similar to another problem in one of the other practice exams. Suppose f of x is continuous on 1 to 4, with f of 1 is minus 5 and f prime of x is greater than or equal to 2 for all x in the interval 1 to 4. Prove that there is at most one x in 1 to 4 such that f of x equals 0. Okay, so I did this exactly as I wrote here in method 1 in the previous problem. And the professor did it method 2 multiple times as well. So take your pick. I feel like my method is more simple and actually makes a lot of sense without having to use Rawls' theorem. So let me go over it again. Since f prime is positive, right, they give us that, it's positive, on the interval 1 to 4, that means f is increasing. Okay? As a result, it can only cross the x-axis at most once as it is increasing from the initial point, f of 1 is minus 5. That makes sense, right? If it's increasing, it'll cross, right? In order for it to cross again, it has to decrease. Or if it's going to rise up to 0, from minus 5 to 0, and it stays flat, the derivative is 0 then, if it's flat, right? but it says it's positive. So it could only cross once. That's what I'm trying to say in method 1. So that's a simple explanation, hopefully. Versus in the professor's method, he or she uses Rawls' theorem, which says if there are two solutions, that means f of a equals f of b equals 0, if the solutions are a and b. Since f is differentiable on 1 to 4 and continuous on closed interval 1 to 4, Rawls' theorem says that if f of a equals f of b, which equals 0, then there exists a c is between a and b, such that, so this should be 1 and 4, okay? Actually, not 1 and 4. Just a and b should be fine. Actually, no, this should be 1 and 4, my bad. Within the interval of interest, these are your solution points. So between 1 and 4, such that f prime of c equals 0. That's what Rawls' theorem says. However, it's given that f prime is greater than equal to 2, or it's never 0 on the interval 1 to 4. Therefore, there can only be one solution. So you can see this one's a little more complicated. Even though it does the job, and maybe you can argue that it's a little more mathematically rigorous, but my explanation worked perfectly fine as well, in my opinion. It's always increasing. So how in the world will it decrease back to 0? Impossible, unless it's flat. But when it's flat, that means the derivative is 0. Okay? Now, prove that there does exist an x in 1 to 4 such that f of x is equal to 0. Hence, what can you conclude about f of 1 minus f of 4? That's the hint. Well, this is exactly like one of the other problems. F of 1 is minus 5. Let's assume that it's increasing at the slowest rate of 2. Assume f prime of 2 is 2 on the interval 1 to 4, the smallest rate of increase, as I just said. Okay, so if it's always 2, it's going to be linearly increasing with a slope of 2, right? So f of 4 would be, at the very least, you start from minus 5, and the rate of increase is 2, right? The slope and the amount of time, per se, or amount of x it's increasing is 4 minus 1, which is 3. Okay? This is, if we simplify the side of the inequality, is 1. Okay? So f of 4 has to be at least 1. We already took the slowest rate of increase. If it's increasing even more, then it'll be more than 1. Okay, so now does this sound familiar now? We found a positive point, and they gave us a negative point. This is intermediate value theorem now. Since f is continuous on 1 to 4, this is a big condition for intermediate value theorem, continuity. F of 1 is less than 0, f of 4 is greater than 0. By the intermediate value theorem, there exists a c is between 1 and 4, such that f of c equals 0. Okay, so same type of problem, exact same type of problem as before in these two questions, actually.